Okay, so first, the tangent line problem you should definitely have nailed by Friday. The sooner the better, so today's good. What's a point at which you are drawing the tangent line? 4, 2. Okay, you obviously need an x and a y. The 2 comes from putting 4 into the square root function, right? The slope, with proper notation, you first need to express, hey, I'm finding the slope by taking the derivative, which you could use dy dx or y prime. There's not really an f here, so f prime, you're kind of on shaky territory, but whatever. Actually, not whatever. Use the notation they give you, excuse me. So what is the derivative by power rule of x to the half? 1/2 x to the negative 1/2 of 4. We typically do this by rewriting this as 1 over 2 times the square root of x, and then saying that at 4 is a lot easier to work with than that negative exponent stuff. So what's your slope? 1 over 2 root 4 or 4, right? Okay. What slope form then? Y minus what? Now you speak. Y minus 2 equals 1/4 times the quantity x minus 4. All right. Now then, actually maybe you won't need your calculator for this. I think I took that part off. All right. Now 7 is just trying to get the concept out exactly what you're doing. It's easy to get lost in a bunch of symbol pushing, especially in calculus, what the whole point is. So always remember, try and think, well, why do you do this? That'll help understand a little thoroughly, or more thoroughly. So the square root function, if you were to graph it, would have 0, 0, 1, 1, 4, 2, 9, 3 as good points on the graph. Tell me, I kind of missed that one. I want it to be accurate. Do you agree? Right. Now the tangent line I just drew is a line, obviously, and it touches at the point of tangency. The point of tangency is 4, 2. And I also found that it has a slope of up 1 over 4, up 1 over 4, or down 1 over 4, down 1 over 4. Okay? You with me? I missed. Dang it. All right. Now my question is, or my point is this. The tangent line is doggone close to the curve right at 4, 2. In fact, it's at the curve at 4, 2. And therefore, it would be a very much the same y values around 4. They're pretty much right on top of each other there. And so because of that, we could use the tangent line to estimate the square root around 4. But the further and further you get away from 4, the further and further the gap between them, and the more error you would get by using a tangent line to stand in for the curve. So my question is this. Just estimate for what region of x values the tangent line is less than 1 unit from the curve. Now that's 1 unit vertically you care about, all right? So ballpark, we would say that the line is within 1 unit vertically of the curve from where to where? What about the left edge? Where does it start being a gap of more than 1 unit? 0. Yeah, it feels like right in here, they're 1 unit away. So after that, the curves start getting further and further. In fact, the square root doesn't even exist there. Kind of off over here, but ballpark estimate. This is, again, just eyeballing. Just what do you think over here? When would it be about a unit away? Doesn't even look like it's on the graph, but so give me a stab at it. 10. Okay, sounds good. Maybe at about 10. So seems like from somewhere from 0 to 10, you're getting a good estimate, and after that, the tangent line would be a really terrible estimate. That's why if I wanted you to, say, use this tangent line idea to estimate the square root of 10, well, you wouldn't draw a tangent line at 4, you'd draw one at where? If I wanted you to use a tangent line to estimate the square root of 10, you wouldn't draw a tangent line at 4, you would choose one at 9. Why not? Because 9 is a good point on the graph, but it's closer to, oops, this would be better, so it's closer to 10, so we'd get a better estimate. And so you always choose a point of tendency close to the one you're interested in. All right. Let's hopefully get good at that by the end of the week. By the speaking of the end of the week, you have a test on Friday. Yay! I'll have a review for you on Thursday. I'll be happy to help you Friday before school if you have questions or you want to review some things. The test is Friday, and I'm feeling it'll go through last week's material, set 28. By Friday, you should be all good on everything through last week, so this is through set 28. If that's not the case, make sure that you get in for some power before now and then. That way, you won't have homework for the fun stuff. That way, what was I going to say? Oh, yeah, that way you won't have homework for the weekend. Hopefully you can just go and get done with your bad self without having to worry about math. All right? So, calculus at 29 differentials. This, in the past, I kind of went too much on this, and it lost me. So, I am toning it down. The first time I taught this, I actually probably taught 7 days worth of stuff in one day, and it was just, it was not good. So, this I'll break up into a couple chunks. I know it comes back later, set 20 or 99 at least, so hopefully it'll go well. The idea, first of all, let's start off with the basic Saxony kind. If it says to find a differential expression analytically by finding the derivative and separating the differentials, that's pretty wordy. First of all, dy and dx are differentials. And as is important to me, I'll just remind you that the dy and dx are notation from Leibniz, one of the creators of the calculus. He used this dy and dx, and he said dy and dx represent the smallest possible positive quantity. And they said, what does that mean? And he was mocked for this, as I think I mentioned. He was mocked for this for 30 years after, the idea of a differential. Turns out this whole thing is really the genesis of all engineering, differential equations. Man, I can't even imagine doing much of the engineering you guys do without differential equations. So he was about 300 years ahead of his time. Genius. So this is the idea. For now, it's going to be a very straightforward process. The D here seems to indicate that they want derivative, right? And that is true. The first step is find the derivative. When I find the derivative, given that it's y notation, that means dy dx is the derivative, the derivative of y with respect to x, if you really wanted to say it long ways. What is the derivative of that right-hand side? What's the derivative of sine? Cosine. What's the derivative of e to the x? E to the x. And what's the derivative of 3 over root x? I'm confused. I'm going to do a rewrite step. 3 over root x is the same as 3x to the negative 1/2 power, right? Yes. By writing it that way, the power rule is a little easier to employ. So use the power rule, bring the power down, drop it by 1. What's my derivative? Negative 3/2 x to the negative 3/2. Subtract 1 from the exponents, negative 1/2 times 1 is negative 3/2. Pretty cool? Okay, the second thing is then to separate the differentials. This is a huge idea of differential calculus that we'll talk about more when we get to integration, but right now it just means that these dy's and dx's, they're separate quantities. They have algebraic meaning. Tiny change in y equals, well, I could split by just multiplying. Dy is that derivative times a small change in x. Right now, it's a lot of symbol pushing, but it has meaning. You could say that the change in y comes from the rate or ratio of change between the two times a change in x. Try the other one on your own, please. supposed to be a comma, by the way, at the end of time, but V naught is a constant. It's a constant. It is not a variable. Now I showed this in 2 steps, but you should definitely do this in 1, especially with our practice. I don't need to see it in 2 steps. I just wanted you to know what I was doing. So, what is your answer? dy is the quantity in parentheses, what? Negative sine of x plus 1 over x plus. Okay, now that's 5v naught times x to the first. That's not a prime, that's a comma. 5v naught just stays out front. So what's the derivative on x to the first? 1x to the 0, and x to the 0 is 1. So this just amounts to 5v naught, right? And then, once I took the derivative, I then moved the dx over, and so outside I have my dx. And what's the vocabulary for dx and dy? They are differentials. It's a tiny, tiny, tiny change in y. All right, now, let's get a little further here. Let's start off with a pre-algebra case here. You've done a million different rate times time problems in your past. Taking different forms even. So, for example, Harper travels 7 feet per second in 8 seconds. 7 feet per second in 8 seconds. Harper travels 56 feet, yeah? Now, whether you know it or not, you could say this is like a rate of change. This is like a derivative times an amount of change in x gives you amount of change in y. You don't even know it, but that's really what you are doing all that time. A rate times a time gives you an amount of change in the other variable. It's calculus. It's just in calculus we use varying rates rather than constant rates like this one. Emma does 4 problems per hour for 7 hours. Her rate is 4 problems per hour times an amount of time, or a change in time. Time changes by 7 hours. That gives you change in problems, or 28 problems. Again, the idea is that this is a rate, and every derivative is like every rate's like a derivative, times an amount of change in time, or maybe dy, or dx rather, gives you this quantity change in problems. Now all this is to say then that every rate times time problem really amounts to a change in one variable. Actually, let's say change in the response variable or change in a y variable has to do with the rate of change in y with respect to x times the change in x. And so in essence then it's dy, or a change in y, has to do with the rate of change, the derivative, times the amount of change in x. 7 feet per second times 8 seconds, that's really a rate times a time. I know it looks fancy, but it's really just a rate times a time gives you an amount of change in some other variable, okay? Now then, let's move this up. Show you how a calculus problem might look like this. So, based on the rate at which y equals x cubed plus x is changing and x equals 2, if x increases by y by 1 unit, how much will y change? Wow, that's pretty stinking wordy. But think of it like this. The rate of change in y at x equal 2. That means the derivative. Yeah? So let's start by finding the derivative. f prime at 2 is, what's the derivative first of all, then worry about the 2. 3x squared plus 1. At x equal 2 then, the rate is 13. Now, that, I'm going to pause and go visual on that. X cubed plus x is a really intensely growing slope or curve. And at 2 then, when I find this 13, think of it as the slope, or change in y over change in x, is 13 units in y for every 1 unit in x. If x changes only 1 unit, y would change by 13 based on that. It's changing, sloping really quickly, right? Now, is the rate of change always that intense, or is it just because the curve is so steep out? Would the slope be that intense closer to the origin? No, okay. I must be doing too much talking because I feel like people are tuning out. All right. So the question then, if x increases by y by 1 unit, how much will y change? Well, we know right there, based on if x changes by 1, y will change by 13. All right. Now, the question is then, all right, is that how much the function really changes when I go from x equal 2 to x equal 3? Well, at x equal 2, we just said y is, what is f at 2? Uh, 10, yeah? Not f prime at 2, f at 2. What is f at 2? It's 10, all right? X at 3. Or sorry, x at 3. What is y at 3? 30. Okay. Now, the true change in y was actually 20. In terms of notation, the true change in y, you could say, is actual delta change in y. The true change in y was 20. And our calculus-y kind of estimate was that it was only going to change by 13. How are we off? We said, at this point, I would expect it to change by 13 units. But it actually changed by 20. Well, it's because the minute you go off of 2, the curve doesn't stay sloping like that. The minute you go off of 2, it starts to get even steeper. And so, although it's a good picture of how fast it was changing at that instant, because it's curving up, it actually changed even more. So, if you were to look at this slope or the derivative at 2, this is the 13 we had expected. 13 is the expected change. At the instant when x is 2, the slope was 13 over 1. I expected that to keep going and y to change by 13 units. The true change was actually that it went from 10 up to 30. Now, that green change, the true change, that's delta y. That red change of 13, that's dy, or based on the change or the calculus change at 2, we would expect it to change by 13. Now, delta y is close to dy when the points are close together. I mean, 13's not great, but it's in a ballpark. if I kept it even smaller, then delta y and dy would be even closer. You can see that the gap, kind of think tangibly, the gap between those gets further and further the more you get away from the point of tangency, all right? So my first point of using differentials is that you can use this calculus amount of change to estimate true change for points close by. And maybe you should put that into plain old words. True change is estimated by the derivative times an amount of change in x. I'll kind of think of it as a rate at which it's changing at this instant times how much I expect x to change gives me an amount of change in y. Now, if you're kind of not really with me, stick with me, and it'll get better, I promise you. Just this the starting introduction that gets a little bit. All right. So, based on the rate at which the square root function is changing at x equals 9, if x decreases by 1 unit, how much, I have this covered, how much will y change? Get it, never mind. You get the idea. All right. Now then, this, I imagine, gets pretty wordy. What am I even supposed to do? So let's start by how much will y change? The true change in y can be estimated with this calculus idea of the difference. And I know it's not quite exactly what does that mean even? Stick with me, right? Let's start by finding the rate at which the derivative is changing, and then say times an amount of change in x, and that'll give you an amount of change in y. The derivative for this function, what is it? What's the derivative of x to the half? 1/2 x to the negative 1/2, or after simplifying, 1 over 2 root x. Now we want the rate of change based on the rate it's changing at 9, so I'm not going to just find the derivative, I want the derivative at 9. Now that rate of change times an amount of change in x will give me an amount of change in y. Now I want you to then multiply that by dx, or the amount of change in x. How much are we changing x by as according to the problem? By what? 1 or negative? I'm doing all the work up here. You guys are just sitting there watching. All right. So I go back by how much? If x decreases by 1 unit, then dx, or the change in x, is going to be -1. Now this 1, what is that derivative at 9? 1/6, okay? That, I know it has a number that flavor to it, but it really means it has a ratio of change. Y will change 1 unit, y will change 1 unit for every x change of 6 units, right? That's a rate of change. I'm changing x by actually -1, and so y will change by -1/6. That actually makes sense. If I decrease x, then I should get a decreased y as a result. If I decrease x by 1, y will decrease by 6. Are you with me so far? Okay, now if you really were brilliant, you could tell me that this implies that the square root of 8 is what? 2n, not 6, 2n 5, 6. Because the square root of 9 is 3, and we would expect by decreasing x by 1 to 8, then y would change by 1/6, or decrease by 1/6, so 3 would go down to 2.56. All right, now, that's to be, let's try more of an application problem here. You need to be this able to, is this the next thing on your notes? Sorry, I didn't, I was pasting while I was teaching. Sorry, I wasn't fully paying attention. All right, we have a lot of applications to this. Let me give you a science kind of one, then a business econ kind of business calc kind of one, and then we'll be good. I measure the edges of a cube. I see that it's 8 centimeters. My ruler's a little deformed. Maybe it's a paper ruler all beat up. So my measurement could be off by as much as a millimeter, or 1/10 of a centimeter. Now, if I then use that edge measure to do some kind of calculation, like find the volume in that cube, well, if I measured a side wrong, wouldn't that mean that my volume would then also have error as well, because it's based on a faulty measurement? So the idea is that we will estimate, use differentials to estimate how far I could be off on calculating volume. Now, first, interpret the question. They want to figure out how much I could be off on the volume. Now, the true amount I could be off on volume is delta V, the true change in volume by being off the vapor. I'm going to estimate that using differentials. Now, differentials here would not be dy. I'm talking about difference in volume. So, dV. dV estimates delta V. All right? Now, the idea we talked about on the previous is the differential is the same as the rate of change times an amount of change in x. Now, in this case, that was the front side, and because we were dealing with a y, x, f of f equation. Now, this has no x's, no y's, so we need to figure out, all right, how does this one work for this guy? Well, dy, that's a y, sorry, dy is going to be replaced with dv. F prime, that's the equation that relates the variables. Now, this is a cube. Give me the equation for volume of a cube. Volume equals x cubed, okay? So instead of f prime, we're going to use, that's true, but what's the derivative of? Is it f or x or v? V, okay, we're going to find v prime and multiply that by dx, or how much off dx could be. So that's what I would like to see is dv is v prime, or the rate of change times an amount of change, which in this case, the amount of change actually is the error, how much x could have been off by. All right, v prime, report the derivative. What is the derivative of v in this case? 3x squared. At what point am I going to find how my rate is changing? It needs to be at a certain point. At x equal. Now I measured it at x equal 8. But the dx, or how much that 8 could be off by, it could be a 10th off. So that error, or x could change by, is plus or minus 0.1. Because it could be a 10th too much or a 10th too little. Plus or minus, right? We're almost there. What is 64 times 3 mentally? 192 times plus or minus 0.1. 19.2 plus or minus, and what are the units? This is change in volume, or how much error in volume you could have. So based on this, it must be centimeters cubed. All right. Now that error then makes for a lot, that small error in length measure actually makes for a huge error in volume. By being off just a 10th here in all 3 directions, think of all that extra volume you would gain by extending that out just a 10th in every direction. You'd have all these little areas of volume. That volume error could actually be quite great. You try. Use differentials to estimate how much the surface area could be off by being off 1/10. Same cube problem. That's the starting point I would like to see. True error in surface area delta x can be estimated by differential dx. On my exams, I expect that. What's your surface area equation? I could do that 2 area of the base stuff. Is there an easier way for a cube? What is it? 6x squared is probably the easier. 2 area of the base plus perimeter of the base times the height would be that equivalent. It's just a heck of a lot easier to use 6x squared than 2 times area of the base plus perimeter of the base times the height. How we doing? Done or another minute? Okay. So what's the derivative of s? Derivative of 6x squared is 12x. We still are doing it at the good point that we think is happening, which is x of 8. But x could be off by as much, and that's dx by as much as 0.1. Think of dx as the delta x, or the error, possible error. That then is 12 times 8, or 96 times 0.1. And so did you get a possible error of 9.6 what units? Centimeters squared. Okay. Last but not least, I think I have a business, so no. I have 2 sets of questions though. I think I'll touch on this later. I need to get on the questions. Questions on. You still have 2 sets of questions, yes? 27 and 28? Okay. Tell me whatever questions you have. These both are new today though. 27 this or 28 that. Tell me. Shout them out. 20, what? On 27 or 28? 27, 17. Shout them out. 27, 1. 24 and 27 or 28? 27, 24. 27 or 28? 27, 14. 27, wait, turn around. 27, 12? 27, 22? They're both going to be due today, so make sure you get your 28 questions answered also. 28. 28 what? 1. Okay. All right. 27, 17.
No, 28, 24.
28 what? 24? Okay, 28, 24. All right. Here we go. Okay. 27, 17. Here we go. The problem is, just like the book, 3717. Okay. Okay, so here goes. Do you need both A and B, or is it just one or the other? Whoever's question this is both. Okay, so for F, because F is a square root function, we can either have negatives. That implies that x minus 1 must be at least 0, which implies x must be at least 1 to get a positive, or at least 0, right? The range you could do one of two ways. Analytically speaking, you could say, what comes out of this? Well, think negatives, positives, and 0. I can't get negatives in the root, so can I get a negative out? No. Can I get 0? Yeah, if I put in the 1, I get out a 0, and then I could also get out positives. And so that tells me F must be greater than or equal to 0. You could also think graphically, if you're a visual person, this is a right shift of the graph, and therefore x is from 1 and up, and range is y is 0 now. For g, f of x, or g of x equals x squared, either analytically or visually, there is no problem with x's. There is no x that would cause that to break, so x is all reals. As far as y's, because it's squared, I can't get a negative out. So I can't get a negative, I can get 0, I can get positives. So the range is that g is greater than or equal to 0. Again, you can use the graph on that one because you do know the graph. All right. B is a little harder. Fog is the same as f of g of x, or in other words, g goes into f. And so it amounts to this. Don't you dare for 1 minute think, oh, I'll just square root each one, and that's x minus 1. That is absolute math garbage. It's nonsense. You cannot square root parts of a sum. So don't even think about it. Domain, I need to figure out what kind of x's would cause this to break math. I start by finding zeros. Where would this be 0? At negative 1 and 1, right? That means everywhere else I'm either going to get a negative or a positive. So think, all right, what about at negative 7? At negative 7, because it's squared, I'd be cool. I'd get a positive in a root. At 0, however, I'm going to have a problem because I'd have a negative in a root. And at big numbers, I overcome that 1, and I'm starting to get positives in the root. So it feels like I'm good at the outsides. X has to be less than or equal to negative 1, or greater than or equal to positive 1 to overcome the subtracting 1. That's called the sign test, or sign chart, and it's useful in calculus. In terms of the range, again, you're asking, all right, not what goes in, but what comes out. And again, I think negatives, zeros, and positives. Can you get a negative out of this? Well, I've taken steps to keep negatives from going in, so I'm not going to get a negative out. Can you get 0 out? Yeah, if I put in 1, I get that 0, and 1's allowed, so we're cool. And positives, obviously, if I put in big old x's, I'll get positive x's or y's. And so it feels like fog, or the outcome, is greater than or equal to 0. Okay. 27.1, is that a question still? Okay. 27.1. I did this maybe a little differently than you did this, so that might be the question. I do a bit of a shortcut here. It says the amount at 1 year is 1.53 million. The amount at 3 years is 3 million. They ask for an equation that describes amount as a function of any time and the value of assets after 7 years in business, so the amount at 7. All right. Now then, the true equation typically looks like this. Yeah, A naught e to the kt. Are we cool? Now, I am kind of lazy, so I do this rather than find amount at time 0. I just don't. Too much work. I just don't like it. So let's use these, shall we? Wouldn't you agree that this is the earliest in terms of time? It started at 1.53 million at time 1, and 2 years later it was up to 3 million, right? So at least in my mind, I'm going to say that if I start at 1.53 million and grow by some factor for some years, well, how many years to go from 1 year to 3 years? That's after 2 years. And after it grows for that factor, what does it end at? 2 years later, it's at 3 million. So you can see that that's not really involving finding the initial amount. I'm just kind of relating the 1 year, 3 year case to a 2 year gap. That means then that the log of 3 over 1.53 is equal to 2k. So k is the natural log of 3 over 1.53 over 2. Are you with me? Okay, I'm going to continue to call that k, so I don't have to write all that stuff, but k has been defined. All right, now, again, being lazy. Rather than call this find a not too much work, I'm just going to say I'm going to use 1.53 million as my starting point and say e to the k. Now, if that's my starting point, then any other point isn't going to just be time since time 0. It's going to be time since time what? 1.53 million is how much at time 1. So that t is not going to really represent t. It's going to represent t since time 1, which is t minus 1. Now, by doing that, it keeps me from having to go back and do all of that substitution, elimination stuff to find a initial. Ooh. Okay, time since time 1. Now, that you'll find works. Check it if you don't like it. At time 3, well, at time 3, it would be 1.53 e to the k times 2. Hey, look at that e. It works. At time 7, then, I would be doing something like this, which is to say 1.53 million starting point times 6 years of growth gives me the 7th year. I know that might not be quite how you learn it in pre-calc, but that's how I would definitely do it in calculus. All right, or maybe it is how you do it in pre-calc. 27, 24, is that a question still? Yes, no? Whoever has 27, 24, do you need it still?
Yes.
Okay, 27, 24. All right, this is not a huge idea of this class. It's just a way back from Algebra 2, I think this was taught. And I got to tell you, if I weren't a math teacher, I probably wouldn't have remembered this at all. The formula comes from similar triangles. It's a big mess. I tried to, on my key at least, give you a hint. The rule is the outside times the whole of segment 1 equals the outside times the whole of segment 2.
Allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
Roll Tide, an elephant for a mascot, notable alum Harper Lee. Learn more about the University of Alabama, who will be visiting with interested students today during 7th hour. Please sign up with the 7th hour app at Counseling and in Navion.
Colorado State University. Students are invited to learn.
So when I say outside, I mean
Bus passes are
just the
available
secant
to be
outside
on
x
pickup. Stop and get yours.
times the whole a plus x equals outside x minus 1 times the whole x minus 1 plus 6.
Seniors, don't miss out on the college essay writing workshop today during 7th hour in counseling. Hear great ideas on how to approach and be successful writing a college essay that shows your passion.
So you're supposed to do this in terms of A, I guess? Is that right?
Seniors, we still have more space for baby pictures. Make sure you submit and pay for your favorite pictures via the yearbook link to the Senior Tribune ad on the Devlin website. You can pay for up to 3 pictures of your favorite childhood memories. You only have 2 more weeks to be involved in the yearbook.
Wow, this is a mess. Did I finish this one? This is maybe that's why you have questions. It's not the setup, it's how you go from there.
Sadly, yeah, come support the boys tennis program tonight from 4 to 8 at the Chipotle on Lawn Forest just north of Hampton. Tell the cashier you're there to support the team.
Okay, so thankfully the x squareds drop out. That allows you to find x in terms of A only. That's all you're going to be able to do. It says solve it for x in terms of A. Okay? And that's just done. Probably should replace that. That's not a big idea of calculus. I don't want you getting hung up on that. Do you have, I will make sure that anything that's not on my key gets added on, this time I really will remember, by lunch. I didn't post a key for 28, did I? Okay. It's 27, I have starts for all these problems. 12, I did 12, 22. Okay, so it feels like my key has most of these 27 questions. They're online. Okay, I'll do those 2. I would add to my 28 key at lunch. Okay, make sure I get those 27 and 28 by the end of the day.